Hi, and welcome again to my Physics Online video lecture series. Today's video, we're going to be talking about energy storage in a capacitor, again from a algebra-based introductory level perspective. So at this point, you've already talked a bit about capacitors and capacitance, and about how capacitors store charge. We already know, for example, the definition for capacitance as C being Q, the charge stored per voltage drop between your two conductors. So now we turn to energy storage. And you know that potential energy is basically the potential for some force within a system to do work within that system. So in some sense, delta U is equal to the negative of how much work is done to get a system into a given state. Or put differently, the work done on the system to get it into a state is then stored as the potential energy of that state. So what that means is this. Suppose that I have a pair of parallel plates, and we'll take the plates to be infinite, but I'm drawing them down here as if they are fitting down here. But imagine that they're infinite and that therefore the electric field between them when charged just runs as a set of horizontal lines. Now let's suppose that I start off with zero charge on either one of these plates. Okay, I'm going to hook these up to a battery, and the battery basically is going to do work. It's going to do work by removing electrons from this plate and moving them really around the circuit to this plate. But as far as figuring out how much work is actually done, that's really equivalent to taking a minus charge and moving it from this plate over onto this plate. And so the first time you do that is more or less like free. There's no field, and so you're not really going against any fields or anything like that. Okay, and then you can move a few charges like that from one plate over to the other without doing very much work. But as you start to build up the charges on these two plates, so now you've removed several charges. This plate has a net positive, this plate has a net negative, and now that means that you have electric fields running between the two plates. So perhaps your field lines look something like this at this point. And now imagine taking that same negative charge off of the first plate and moving it over here onto the second plate. Well, you're now having to push that against the force that this field would be applying to it. Essentially, the field is from left to right. That means that the force applied to a negative charge is from right to left. Put differently, in moving a negative charge onto this plate, you're actually moving a positively charged hole over here to this plate. So each time you move a negative from one to the other, you also move a positive from the second one to the first one. So this scenario basically means you're having to now do work against the field. And as you build up more and more charges on these two plates, that field gets stronger and stronger. Again, recall that the electric field strength E is given by sigma over epsilon, where epsilon is or epsilon naught is the permittivity of free space, or 8.854 times 10 to the minus 12 farads per meter. And so each time that you've moved some charges from one to the other, now there's a little bit more sigma, because sigma in turn, let's just write it up here, sigma is defined as charge per unit area. So each time that I build up a little bit more charge from one plate to the other, I've also increased Q. The area is staying the same. That means that I've built up sigma a little bit more. Okay, so that basically means that each time I move another charge, I have to do just a little bit more work to move the next charge over. And so one way that we go about handling that is we could, for example, make a plot. And that plot basically would show on one axis how much charge has been moved, let's say, from one plate to the other. So Q is the charge now on each of the two plates. And on the other axis, what I have is how much electric field is there, but again, given that we have a fixed distance between them, we could write this as delta V, which is equal to E times D. And if I were to plot these two things versus each other, what I'd end up getting is basically some sort of a straight line like this. All right, and now what I want to know is how much work has been done by this system. And so to get that, I can essentially use the fact that delta V times Q, when both are constant, gives me work. And so if both are changing, that is equivalent to finding the area underneath this curve, or underneath this line. So if I wanted to move from, let's say, Q naught to Q final, then whatever the area right here is, that would be how much work is done. So this represents work done in moving delta Q is equal to Q final minus Q initial from one plate to the other. Again, assuming that we are beginning from Q naught. And so, in other words, this area is what is giving us this. And okay, so now we say, all right, we don't want to just find work, we want to find the potential energy. And to do that, what we do is, again, we duplicate this plot again. Whoops. And again, we have down here Q, and again up here we have delta V, which is E times D, which, if you were to go back through here, Q is sigma times A, and E is sigma over epsilon naught, and that means that this delta V, that's why it's linear with Q. So this right here should equal Q divided by A all times D over epsilon naught. Okay, and so that, since D, A, and epsilon naught are all constants, that's what gives us this nice linear fit. So if I want to find how much potential energy is stored, then I need to figure out how much work was done in getting from Q equals 0 to actually how much charge Q is stored, or Q final, or whatever. And so that is the area then of this triangle. And area of the triangle, this is delta U, area of the triangle is half of the base, which would be essentially Q final, times the height, which is delta V. or delta V final. So if I do a little dash line over here, we could call this delta V final. So this would be U final. And now we can recall that this is just kind of a placeholder way of writing these things. So U in general should look like 1/2 Q times delta V. So that's how much energy is being stored by your capacitor. Now, going back to our original C is Q over delta V, we can substitute. So C is Q over delta V. We can either substitute this into our equation by saying therefore Q is C delta V, and so substitute this in for Q. Now you have U is equal to 1/2 C delta V squared. And similarly, we could rearrange this equation to say that delta V is Q over C, and so we could substitute in for the delta V, and that means that U is 1/2 of Q squared over C. So this is how much energy is actually being stored by your capacitor. A further note about all this, I've made use of the electric field in finding all this. Essentially, I've said that U was, let's say that we come over here and do 1/2 C delta V squared. So U is 1/2 C delta V squared. But remember that the electric field is related to the voltage. Delta V equals E times D. And so that means that U is 1/2 of C times E delta D squared. And so that in turn means that I have 1/2, I don't really need to call it a delta D, it's just the distance between the two plates. 1/2 of C D squared times E squared. And so in some sense we could say energy is stored in the electric field. So energy is stored in a capacitor's electric field. And we now even have the form for which that is done. There is a similar term called energy density. So if little u is energy density, that would be energy per unit volume. Excuse me. Then I could divide the big U by the volume and get this energy density. As it turns out, when I do that, bearing in mind that the volume, I'm going to use a V with a little kind of line through the bottom of it. The volume would be area times distance. And remember that capacitance is area times epsilon naught divided by distance. And so if I am dividing U by area, I have an expression like this, where I have basically substituted in the volume right here, little u being defined as big U divided by volume. And I've substituted in here for the capacitance. So now I can cross off, I've got a D and a D and a D squared, so those cancel. I've got an A and an A, those cancel. And so what I'm left with for my little u is that little u equals 1/2 epsilon naught E squared. And that's my energy density.